All right. Excuse me. Today we are going to be talking about power relationships for steady state sinusoidal circuits. And the first that we're going to talk about is what's called the instantaneous power. So let's say that we have following generic circuit where we have a voltage source that is supplying a linear black box network. Containing potentially resistors, inductors, and capacitors. There will be a voltage drop across this network, which I will call V of t, and a current flowing into this network I'll call I of t. And if Vs of t is of the form V naught cosine omega t plus some phase angle phi, then we should observe that V of t will be of the form Vm cosine omega t plus theta v, and I of t will be of the form Im cosine omega t plus some phase angle theta I. So effectively, all I'm trying to set up here is that if we excite this linear black box network sinusoidally, we should see that the voltage drop over the network is a sinusoidal voltage having a particular magnitude, frequency, and phase angle. And the current flowing into the network will be a sinusoidal signal having a particular magnitude, frequency, and phase angle. Excuse me. The power absorbed by our network as a function of time will simply be the product of the voltage and the current, or Vm cosine omega t plus theta v multiplied by Im cosine omega t plus theta I. Using trig identity number 9 from our sinusoidal review lecture, I can express the product of two sinusoids as 1/2 the cosine of the difference of the angles plus 1/2 the cosine of the sum of the angles, which in this case is going to look like 1/2 Vm Im cosine omega t plus theta v minus omega t minus theta I, leaving just theta v minus theta I in this term. And then I will have a 1/2 Vm Im cosine, twice omega t plus theta v plus theta I. So this is our expression for the instantaneous power that is being absorbed by this linear black box network. If I were to plot this function, it may look something like this. So here is P of t, here is t. Good straight line. So my power may look something like this. Which is just a sinusoidally varying signal, but it has some associated offset power. What that offset power is the DC contribution to the instantaneous power, and then superimposed on top of that DC contribution is this sinusoidal waveform, where this sinusoid is actually operating at twice the frequency of the voltage signal and twice the frequency of the current signal. So we have these two signals kind of added to each other, giving us the instantaneous power. Now, let's get a little bit more specific here. We have a generalized case. Let's talk about what happens if we just have a resistor, right? So in a resistor, R having some voltage drop V of t across it and some current I of t flowing through it. Hopefully you guys can recall from our phasor relationships that we had V phasor was equal to I phasor times R. And we found out then that the magnitude of our voltage Vm was equal to R times the magnitude of our current. And we also found out that theta V was equal to theta I. So using these relationships, the power absorbed by a resistor becomes 1/2 Vm, actually, hold on, Vm squared over R, where I'm using that relationship. What I'm trying to do here is express everything in terms of voltage quantities. And then I'm going to have cosine theta V minus theta I. So what is cosine theta V minus theta I in the case of a resistor? Anybody have any thoughts?
Would it not just be 1? Because since theta V and theta I are equal to each other, that would go to 0, and cosine of 0 is 1.
That is exactly correct. So since theta V and theta I are identical quantities, cosine of 0 gives us 1. So we're just going to have that term. So what I'm actually going to do here is I'm going to have that 1/2 Vm squared over R times 1 plus, and now I'm going to have my second term, twice omega t plus twice theta V. So that's expressing my instantaneous power absorbed by my resistor in terms of only parts of the voltage waveform. I can also do it for the current waveform, where I would have 1/2 Im squared times R times 1 plus cosine twice omega t plus twice theta I. So these are analogous to the relationships PR is equal to B squared over R and PR is equal to I squared times R that we saw in this value is going to be different, but they do have a relationship in there that is similar. There's a factor of 1/2 that we have to worry about, and there's also that AC term superimposed on top. So it's loosely familiar, but there's a little bit more that we need to pay attention to. All right. For an inductor, where we have some inductor having a value of L with some voltage across it and some current flowing through it. If you recall, our phasor relationship was V is equal to J omega L times I. So we saw that the magnitude of the voltage was omega L times Im, and the phase angle of the voltage was equal to the phase angle of the current plus 90 degrees. We would have PL of T is equal to 1/2. So let's see, Vm squared over omega L. And now we're going to have cosine theta V minus theta I. Okay. So when we do cosine theta V minus theta V we know to be theta I plus 90 degrees minus theta I. This is just going to be cosine of positive 90 degrees. What's the cosine of positive 90 degrees?
0.
0. Absolutely right. So that whole first DC term is going to go away. We're not going to have it at all. And then we're going to have cosine twice omega t plus twice theta I, excuse me, theta V minus 90 degrees. And similarly, expressed in terms of only the current relationship quantities, we'll have Im squared times omega L cosine twice omega t plus twice theta I plus 90 degrees. For a capacitor, where we have some capacitor having a value of C with a voltage V of t across it and a current I of t flowing through it. We know that our phasor relationships was J omega C times V phasor was equal to I phasor, which gives us the relationship Vm is equal to Im over omega C. And we also saw that theta V was equal to theta I minus 90 degrees. So our instantaneous power absorbed by a capacitor then becomes 1/2 Vm squared omega c. And then we're going to have cosine theta v minus theta I. So that's going to be theta I minus 90 degrees minus theta I looks like cosine of negative 90 degrees. What's the cosine of negative 90 degrees?
Should still be 0.
Also 0, absolutely correct. So our DC term goes away, and we're left with cosine twice omega t plus twice theta v plus 90 degrees. And in terms of our current quantities, Im squared over omega c, cosine twice omega t plus twice theta I minus 90 degrees. So there's a couple of interesting things that we can unpack from this, okay? For a resistor, let's call this guy PR of T. And here is T. Our power waveform is going to look something like this. Actually, hold on. It's not correct. Okay. So the value of our instantaneous power for a resistor will always be 0 or greater. What that tells us is that in an AC circuit, our resistor is always absorbing power. It is never supplying power, which makes perfect sense because all a resistor can do is convert electrical energy into heat. It has no means by which to store energy, so it shouldn't ever be able to supply power to our system. It has a DC offset quantity that is exactly 1/2 Vm squared over R, or 1/2 Im squared times R. And then it oscillates from, so effectively it goes to double this quantity down to 0 and back and forth over and over and over again. So this peak value right here is Vm squared over R, or alternatively Im squared times R. Okay. For an inductor, and I'm playing kind of fast and loose with the phase angles here, just to illustrate some stuff. Here's T. Here is PL. We should observe that the inductor behaves approximately like this. Might be shifted in time some, but generally speaking, it's going to look something like this. Exactly half of the time, it is absorbing power, and exactly half of the time, it is supplying power back into our system. Okay. Its peak value is going to be 1/2 Vm squared over omega L, or 1/2 Im squared times omega L. So it's just a simple sinusoidal function, and it has no DC term. And then our capacitor waveform is going to look pretty much exactly like our inductor waveform. We'll have a different phase angle, but it'll behave in exactly the same way. Right. So exactly half of the time it's absorbing power, the other half of the time it is supplying power. So how do you guys feel about these relationships thus far?
I'm not terrible.
Not super terrible. That's pretty reasonable. It's a little tedious. We're about to work an example problem where we're going to do some calculations here, and I'm going to point out some very common pitfalls or mistakes that I see that students make. And then after we get through that, we're going to talk about the quantity average power, and then we'll actually be done for the day. All right. So for my example, find it here real quick. There we go. So let's say that I have the following circuit. I have a current source, IS of t, a 1 kilo ohm resistor, and a 15 millihenry inductor connected all in parallel like so. Current IS of t is 0.1 cosine 2 times 10 to the 5 t milliamps. And what I want to do is to determine the power being absorbed by the source at t is equal to 10 microseconds, the power absorbed by the resistor at that same time, t is equal to 10 microseconds, and the power absorbed by the inductor at t is equal to 10 microseconds. All right. So which of these three things do we want to take a look at first? Anybody have any thoughts?
I guess probably the source first.
Okay. So the power absorbed by the source would require us to know the voltage drop over the source. So let's call that Vs of t. And that voltage drop over the source, Vs of t, will also be the voltage drop over the resistor and the voltage drop over the inductor, because everything is connected in parallel. So how might we go about determining that voltage Vs of t?
Could we plug in 10 microseconds to our IS of t equation? And then that would give us a current, and then I guess we could probably find the current on the 1 kilo ohm, like the current drop on the 1 kilo ohm resistor. And then since the voltage is going to be the same, something like that.
All right, so I understand your logic there and your reasoning. You're not far off from what I would do, but let me think of how to put this. Okay, so we have a circuit that is being excited sinusoidally, and we are trying to find a voltage. Now we're trying to find a voltage at a very, by your way, at a very specific instant in time, and there's nothing wrong with that per se. But my question is more generally, how would we approach this if we were worried about the voltage not at a specific point in time? So what I'm getting at here is, if we try to work this problem in the time domain, it's going to bite us in the butt in as much as we're going to have to do a bunch of trig relationships and all that kind of crap again, right? Instead, let's work the circuit in the frequency domain, because if we look back at these representations here for our power for all these different things, right? So this general case, which would work for our source, we have Vm and theta V and Im and theta I. That's just the magnitude of the phasor voltage and the phase angle of the phasor voltage, and then the magnitude of the phasor current and the phase angle of the phasor current. So even though we're trying to determine a time domain quantity, it's still going to be of the best use of our time to analyze this circuit in the frequency domain and then just take the bits and pieces of information that we need. Does that make sense?
Yeah, I see what you're saying.
So to get those bits and pieces of information, we need to convert this guy from the frequency domain to the time domain. So we're going to have our phasor current, our resistance, and then the impedance of our inductor. So somebody tell me how I can represent that current IS of t as a phasor quantity. What's the phasor representation of that waveform? At this point, that conversion should be pretty much trivial for you guys. All right.
Would it be 0.1? Are you want like 0.1 with an angle of 0 or?
Exactly what I'm looking for.
Oh, okay.
0.1, angle 0 degrees amps. That's the phasor representation. All right. We are trying to find our phasor voltage Vs. What is the impedance of the resistor going to be?
1 kilo ohm.
1 kilo ohm. Okay. And what is the impedance of the 15 millihenry inductor going to be?
J times 2 times 10 to the 5 times 15.
Times 10 to the minus 3, which would look like
Yeah.
3 kilo ohm. So now that I know that, how do I solve for Vs?
Ohm's law.
Sure, that's exactly how I would approach it. 0.1 angle 0 degrees amps multiplied by the parallel combination. So that would be 1 kilo ohm times J 3 kilo ohm divided by 1 kilo ohm plus J 3 kilo ohm. Take a moment to do that calculation and tell me what you get.
I got 0.094 with an angle of 18.43.
So 0.094 with an angle of 18.43. So I'd be willing to bet there that you used ohms as your units instead of kilo ohms. So you did 0.1 times 1 times J3 over 1 plus J3. So to get that, like right now, that would be kilovolts. To get that to regular volts, actually, hold on, let me think about that. Yeah, we need to multiply by a factor of 1,000. So you should be getting 94.868 with an angle of 18.435 degrees volts. So we got the same answer, but yours is off by a factor of 1,000. So make sure to pay attention to the units and stuff like that, or you can make simple mistakes. So from this, we could easily see that Vs of t would be 94.868 cosine 2 times 10 to the 5 t plus 18.435. Sorry, that 5 looks terrible. Degrees volts. So I believe the suggestion was for us to calculate the power absorbed by the current source first, right? So in that case, PCS as a function of time will be 1/2 times the magnitude of the voltage, which is 94.868 volts, times the magnitude of the current, which was 0.1 amps. Oh, I'm sorry. You may have been correct. I meant to do this not as milliamps, but as amps. That's entirely my fault. I think you were actually right, and I made a mistake at the beginning. Sorry for questioning your math. So 94.868 volts times 0.1 amps times 1/2. Then we're going to have cosine of theta V, which was 18.435 degrees, minus the phase angle of the current. And here's where we need to pay a little bit of attention, okay? I say that because if we're calculating the absorbed power, then we want the current that is flowing into the positive polarity terminal, which is in the opposite direction of IS of t. So what should my phase angle be when I'm looking at that current flowing in the opposite direction?
$90.
So 90 degrees isn't in the opposite direction, that's in an orthogonal direction, or 90 degrees out of phase, right? So we want it to be 180 degrees out of phase because it's in the completely opposite direction, right? Because 180 degrees represents, we look at our plane here, real and imaginary. If we go 1 unit out in this direction, we have 1 angle 0 degrees. So in the opposite direction would be 1 angle plus or minus 180. So I'm going to put 180 degrees right here. And then down here, I'm going to add the AC portion. That's going to be 1/2 94.868 volts times 0.1 amps cosine of twice omega t. That's going to be twice 2 times 10 to the 5 10 microseconds. And I'm about to do another conversion here, and it's very, very important, okay? Omega is measured in radians per second. So I need to convert that to degrees per second in order to add my phase angle in, right? Because if I try to add radians and degrees at the same time, it's not going to work out well for me. So my conversion factor here is going to be 180 degrees per pi radian, which is going to give me my angle in degrees. And then to that, I'm going to add theta V, which was 18.435 plus theta I, which was 180 degrees. So I know that this is a big calculation, so I would suggest that we kind of break it up into parts here. All right, so I'm going to do the DC part first. 0.5 times 94.868 times 0.1 times the cosine of 18.435 minus 180. I get negative 4.49, actually negative 4.5 would be closer. So that's my DC contribution. And then for my AC contribution, I get 0.5 times 94.868 times 0.1 times the cosine of 4 times 10 to the 5 times 10 times 10 to the minus 6 times 180 over pi plus 18.435 plus 180. That part comes to be 1.806 watts. And when I combine these two things together, I get negative 2.693 or 2.694, rounding correctly, watts of power absorbed by our source at t is equal to 10 microseconds. So take a moment to do that calculation yourself and verify that I got the correct answer, please.
I got the same thing.
All righty, that's fantastic. So which component do you want to find the absorbed power, instantaneous power of next?
Probably the resistor.
All right, so for the resistor. So we know the voltage drop across the resistor, so we don't actually need to bother with figuring out the current at all, right? I'm going to use the relationship 1/2 VM, actually, sorry, VM squared over R times 1 plus cosine twice omega t plus twice theta V. So that I don't have to bother doing current division or any of that kind of junk to figure out what that resistor current is. So in this case, 1/2, my voltage is 94.868 volts squared divided by my resistor value of 1 kilo ohm. This is going to be multiplied by 1 plus cosine of twice 2 times 10 to the 5, 10 microseconds times 180 degrees over pi plus twice of 18.435 435 degrees. And so let's throw this guy in our calculator. So that first part to me looks like 4.5 watts. And then I need to multiply that by 1 plus. So let's see, cosine of 4 times 10 to the 5 times 10 times 10 to the minus 6 times 180 over pi plus 2 times 18.435. So it's 1 plus negative 0.0688. Which I get to be 4.190 watts. Could please take a moment to verify that that is the correct answer.
I got the same thing.
All right. So before we calculate the power absorbed by the inductor, and we can do it a long way or a hard way, let's look at what's happening here, okay? So if our resistor is absorbing 4.190 watts of power, and our current source is only supplying 2.694 watts of power at this particular time, our expectation here is that our inductor needs to be supplying the remaining amount of power, right? So in an AC system, we're going to see that exactly half of the time our inductor supplies power and exactly half of the time it absorbs power. So there, depending on the size of the inductance and stuff like that, there will be particular points in time where our source is actually going to be absorbing power from our inductor. So our source is going to act like a load to the temporary energy storage element of the inductor. So let me scroll up real quick here to kind of show you what I'm talking about. So when I made this graph right here for our generic load, everywhere above the horizontal axis, which I'm coloring in here in red, our load is acting like it's absorbing power. But everywhere below the horizontal axis, so for these small time intervals, our load is actually supplying power back to the source. So it should not surprise us to see that at this particular point in time, our inductor is effectively supplying a reasonably considerable amount of power to our resistor. So to calculate our inductor power, we're going to be using the relationship 1/2 Vm squared over omega L times cosine twice omega t plus twice theta v minus 90 degrees. And so that's going to be 1/2 94.868 volts quantity squared divided by 2 times 10 to the 5 times 15 times 10 to the minus 3. And we're going to have cosine 2 times 2 times 10 to the 5 times 10 microseconds times 180 degrees over pi. Let's see, plus twice 18.435 degrees minus 90 degrees, close parentheses. And so let's see what this looks like. So 2 times 10 to the 5, 15 times 10 to the minus 3. 1.5 watts times cosine 4 times 10 to the 5, 10 times 10 to the minus 6, 180 over pi, plus 2 times 18.435 minus 90, negative 0.998. And so when I multiply those two quantities together, I get negative 1.496 watts. What I should observe is that PS of T plus PR of T plus PL of T is equal to 0. So if I added these quantities together, negative 2.694 plus 4.190 plus negative 1.496, I get 0. So that's a simple way that we can check our answer there. Make sure we didn't make any mistakes, as if all of the powers absorbed are equal to 0, then the law of conservation of energy is conserved and we haven't made any mistakes. So any questions regarding that particular problem? I genuinely believe that a problem like that might actually be a little harder than what I would test you on. All right, nobody's saying much of anything, so let's move on to the concept of average power. All right, so if x of t is a periodic function, then the average value of x of t can be found by integrating our signal x of t over exactly one period, and then dividing the results of that integration by the length of the period. So our instantaneous power is a periodic signal. So the average value of the power absorbed by a generic load quantity would be 1 over the period, the integral over one period of E of t, which going to look like the integral over one period of 1/2 Vm Im cosine theta v minus theta I plus 1/2 Vm Im cosine twice omega t plus theta v plus theta I. So I have two distinct portions of my instantaneous power, and so I'm going to split this integral up. So I'm going to say that I have 1 over t, the integral from 0 to t of 1/2 Vm Im cosine theta v minus theta I dt plus 1 over t times the integral over one period of 1/2 Vm Im cosine twice omega t plus theta v plus theta I dt. Is everybody okay with what I've just done, splitting that integral into two distinct parts?
Yes, sir.
All right. So what happens when I integrate the first part? Anybody have any thoughts?
Could we treat VM and IM, like could we pull out 1/2 VM and IM?
Not only can we pull out 1/2 Vm and Im, we can also pull out cosine theta v minus cosine theta I, because all of those are constant quantities. So we would wind up having sorry.
So that would be literally just 1/2 VM IM, because the integral of dt would just be t, and then you have that 1/2 out front, so that cancels it.
Right, so we'd have 1/2 Vm Im cosine theta v minus theta I times 1 over t integral from 0 to t of dt, where this guy right here is just 1, which is what you were saying. Right, because we would have 1 over t multiplied by capital T, or 1 over capital T multiplied by capital T just gives us 1. So I can throw away all this part right here. Now, what happens when we integrate the second portion? Any thoughts?
You can pull out everything but the cosine of 2 omega t, and then do you have to leave the theta v and theta I in there?
Yeah. So you're absolutely right. So I'm gonna let's write that down here. 1/2 Vm Im times 1 over t integral from 0 to t of cosine twice omega t plus theta v plus theta I dt. So I want to look at what that integration gives us. So for the sake of argument here, I'm going to say that theta v and theta I are 0 degrees. It doesn't actually matter at all what those particular phase angles are. That sum of theta v plus theta I is just going to tell us how much we shift our cosine function to the left or to the right. So if I have a generic cosine function, like so. And I'm integrating over exactly one period. What is the result of that integration?
I'm gonna be honest with you. I don't know. I don't like taking integrals of sine and cosine.
All right, so we have a cosine function exactly, and we're taking the area under the curve over exactly one period. Half of the time, the area is positive, and the other half of the time, the area is negative. And the amount under the positive portion is exactly equal to the amount of the negative portion. Does that make sense?
So it just somewhat to be 0.
Exactly right. This whole bit right here is 0. So we have 1/2 VMIM times 0. So that bit goes away as well. So from this, our average power is just 1/2 VM IM cosine theta V minus theta I. So I'm going to scroll back up to the top here real quick. What we found was that the DC portion of our instantaneous power represents the average power delivered to our load. And if we look at the graphical relationship, this should make sense because exactly half of the time our instantaneous power is above our DC contribution, and exactly half of the time it's below our DC contribution. So that DC portion of our instantaneous power is exactly our average power. So let me scroll back down here. From this, that's our generic representation. What if we have a resistor? What should the average power absorbed by a resistor be? So our instantaneous power was of the form 1/2 VM squared over R times 1 plus cosine twice omega t plus twice theta V, excuse me. We throw away the AC portion and we're just left with 1/2 VM squared times R. Or we had our current based relationship. And again, we throw away the AC portion. We're just left with 1/2 IM squared times R. So our average power in an AC circuit is just 1/2 times what we would get in a DC circuit for a resistor specifically. What if we have an inductor?
Would it not be 1/2 VM squared over omega L?
It would not be. So we'd have 1/2 VM squared over omega L times the cosine of twice omega t plus twice theta v minus 90 degrees. This cosine term goes to 0, which means we have 1/2 Vm squared over omega L times 0 is equal to 0. Similarly, 1/2 Im squared times omega L cosine twice omega t plus twice theta I plus 90 degrees. The AC term is 0, and since the average power absorbed by an inductor is all an AC term, 0. And crap, for a capacitor, it's also 0. I'm not going to bother crossing out the cosine function again because it should be pretty trivial at this point to see. So we can see that also directly, scrolling back up here, in these graphs, right? So the DC portion of our average power absorbed by a resistor is this stuff right here, which is exactly the relationship that we got by setting our AC term to 0. Well, for the inductor and the capacitor, there is no DC offset, right? The DC, or another way to put it is the DC offset was 0 watts. So the average power absorbed by an inductor and the average power absorbed by a capacitor must then also be 0 watts. All right, so we've effectively wrapped up about 45 minutes early. So what I'd like to do just real quick is I want to take a look at the web work assignment associated with this lecture material to just see if there's anything in particular that jumps out at me. So if I'm not mistaken, this would be homework set number 22. The first problem is simply doesn't even have anything to do with power. It's just a steady state sinusoidal circuit analysis problem. You're given a circuit, you're told what omega is, and so you need to convert the circuit from the time domain into the frequency domain, and then solve for a particular value of current and a particular value of voltage, and then find a time domain current as well. So we, to my knowledge, have beaten that pretty well to death. Problem number 2 is effectively the exact same thing as the example problem that I worked out a little while ago. Literally, current source in parallel with a resistor, in parallel with an inductor, and you're analyzing the circuit at t is equal to 1.1 milliseconds and trying to find the power being absorbed by all three of those quantities. So it's literally the exact same thing, just with different numbers. Problem 3 is a steady state sinusoidal circuit analysis problem where you're asked to find the average power delivered to the impedances. So let's take a look at this problem. We'll use this as an example for calculating average power. So homework 22.3. We have the following circuit. We have a 11.8 angle negative 104 degrees volt source connected to an impedance that is 6 minus J8 ohms. Then we have an impedance up here that is 4 plus J2 ohms. Then we have an impedance here, which is 8 plus J7 ohms. So, since none of these impedances are purely resistive, purely capacitive, or purely inductive, we're going to have to use our generic equation, which means we're going to need to know both the phasor current and the phasor voltage across these guys. So I'm going to call this voltage VA, this phasor current IA. I'm going to call this VB, phasor current IB, and this guy VC, with a phasor current IC. So how would you guys like to go about solving for any of these 6 quantities?
Could you could you not just go ahead and solve for all the voltages by doing voltage division?
That I can solve for VB and VC using voltage division, but I don't think that I can solve for VA using voltage division. The reason why I say I don't think I can solve for VA using voltage division is because the voltage isn't being divided, right? So our 11.8 angle negative 104 degrees volts source is connected directly in parallel to that 6 minus J8 ohm impedance. So I would argue that we could say that VA is just 11.8 angle negative 104 degrees volts by inspection. Sorry. Using voltage division, I could say that VB is 11.8 angle negative 104 degrees volts times, so my denominator is just going to be 4 plus J2 ohms. My numerator is 4 plus J2 ohms. My denominator is 4 plus J2 plus 8 plus J7. So if I toss that into my calculator, I get 4 plus 2i in the numerator, and let's see, that's going to be 12 plus 9i in the denominator. 3 point angle negative 114.305 degrees volts. And VC, I could either get using voltage division, or I could say that it's VA minus VB. Which I get to be 8.362 with an angle of negative 99.684 degrees volts. So we've solved for all three of our voltages. How might we go about solving for all three of our currents?
Could we not just take the voltage that we found and multiply it by the, maybe take VA, multiply it by 6 minus JA to get the current IA?
You are incorrectly applying Ohm's law. So your intention is correct, but
I
Ohm's
know,
law,
sorry.
yeah, Ohm's law says that I should be V divided by Z. So IA would be VA over 6 minus J8, which I get to be 1.180 with an angle of negative 50.870 degrees amps. IB would be VB over 4 plus J2, which I get to be 0.787 with an angle of negative 140.870 degrees. And IC has to be exactly equal to IB because they represent the same current. So that would be 0.787 angle negative 140.870 degrees amps. So the average power absorbed by the 6 minus J8 ohm impedance would be 1/2 times the magnitude of the voltage, which was 11.8 volts, times the magnitude of the current, which was 1.180 amps, times the cosine of the angle of the voltage, negative 104 degrees, minus the angle of the current, which was negative 50.870 degrees. And so let's just do the math there. 1/2 times 11.8 times 1.18 times cosine of negative 104 minus negative 50.87, 4.177 watts. For element B, same exact equation, 1/2 times the magnitude of the voltage. So that would be 3.518 volts. Magnitude of the current, 0.787 amps. Cosine of theta V, so that's negative 114.305. Minus the angle of the current, negative 140.870 degrees. Throw that into our calculators. I get 1.238 watts. And then for the average power absorbed by the 8 plus J7 ohm impedance, I would have 1/2 times 8.362 volts times, let's see, 0.787 amps cosine of negative 99.684 degrees minus negative 140.870 degrees. And that should be 2.475 watts. So that homework problem, fairly straightforward. And that is extraordinarily representative of something like I would put on the test. When we get into what we're going to talk about in Thursday's class, which is complex power, instead of asking you to determine just the average power, I might ask you about some other portions, but homework 22 problem number 3 is pretty much right at the difficulty of the power calculations that I would ask you to do legitimately. And if you look on the practice test that I've uploaded, you'll see that I'm not being facetious here. So let's look at problem number 4. Problem number 4 can be a little difficult. So we're going to look at one part of it. We are given a waveform and we are asked to calculate the average power. So in part A, we are given the following waveform. Here is the time. Here is IA of t measured in milliamps. Our time is measured in milliseconds. And our waveform looks something like this. So it goes down to, this is going to be negative 16 for 1 second, increases to negative 9, stays at negative 9 for 1 second, and then goes up to 0. And this just happens over and over and over. Okay. So we are told that we're trying to find the average power delivered to a 235 kilo ohm resistor by this particular periodic waveform. So how do you think we're going to approach this? Anybody have any thoughts? This is up there with some of the hardest problems that you guys have been asked in any of these homework assignments.
Then you need to find what the period is, big T.
Okay, so that is definitely going to be one portion of it. So what do you believe the period to be? So let me be clear. This is 1, 2, 3, 4, 5, 6, 7, 8, 9.
3 milliseconds.
All right, so you're measuring from here to here. That's big T. And that is exactly 3 milliseconds. Okay, so that's a great start. So
Don't you need to find also the area during that period,
so
the integral?
yes and no. And so what I mean by that specifically, we know that the average power, P average, is 1 over T times the integral of 0 over T of the instantaneous value of the power, right? But the area under the curve here isn't our instantaneous power. It is the current flowing through our resistor. So how do we get, what's the relationship between the current flowing through the resistor and the power being absorbed by the resistor? That's the piece of information that we're missing here. Any thoughts?
No.
All right. So power is always and since power is always voltage times current, we can use Ohm's law to express our voltage as just I times R, giving us I squared T times R dt, or R over T times the integral over 1 period of I squared. Based on knowledge of how circuits behave.
But we still don't know what a function for I is.
It's that waveform that we were given. That waveform in blue is I of t. So we're going to have to develop a mathematical expression for it to put into our integral, which in this case is going to be fairly straightforward. So our average power P average will be kilo ohms divided by our period, which we found to be 3 milliseconds, times the integral over 1 period. Okay, so this is a piecewise function. So I'm going to split my period up into 3 distinct portions because my waveform is made of 3 distinct portions. So over the interval from 0 to 1 millisecond, what is the value of my current?
Minus 16.
Negative 16 milliamps, and I need to make sure that I square my current, and then I have my dt here. Then I have my next integral. It's going to be from 1 millisecond to 2 milliseconds. What's the value of my current over this interval?
Minus 9.
Negative 9 milliamps. Need to make sure I square my current. And then my third portion is going to be from 2 milliseconds to 3 milliseconds. What's the value of my current over this interval?
0 milliamp.
0.
That's it. And I know this part right here is going to go to 0. I didn't actually need to write it, but I wanted to make sure that you guys understand that I am actually integrating over exactly one period. So from here, I'd have 235 kiloohms times 3 milliseconds. And then I'm going to have 16 milliamps times 16 milliamps is going to look like 196 times 10 to the minus 6 amps times the integral from 0 to 1 millisecond of dt. And then I'm going to have negative 9 milliamps times negative 9 milliamps is going to be 81 times 10 to the minus 6 amps. Sorry, amps squared. Times the integral from 1 millisecond to 2 milliseconds. That other part goes to 0. So let's see, 235 kiloohms over 3 milliseconds times 196 times 10 to the minus 6 amps squared. 1 millisecond minus 0 seconds is going to look like 1 millisecond plus 81 times 10 to the minus 6 amps squared. 2 milliseconds minus 1 millisecond also looks like 1 millisecond. So this cancels out those units, and I have kiloohms times amps squared, which should be watts, right? So it's going to be 235 10 to the 3 over 3 times 196 times 10 to the minus 6 plus 81 times 10 to the minus 6. $21.6983 repeating watts.
Yeah, I got like 15 something.
So hold on, 235. So according to WebWork, I didn't get the answer correct. You got 15 something. So let's see what mistake it is that I'm making here.
And that was, I put in the equation right above the 235 over 3 times 196, all that. Like I kept the 1 millisecond in there and then converted everything to base units.
So let me make sure 16 times 16. Oh, there we go. 16 times 16 is 256, not 196. So I was doing 14. So that's one problem, is that I can't multiply correctly. I strongly believe that 9 times 9 is 81. So I'm not going to double check that. Let me see what happens when I put 256 in here. 26.3983 repeating, which is the correct answer. 26.3983. There we go. Yeah. So my methodology was correct. I just can't multiply 16 times 16 apparently. I should have known what that is, but anyway. So Mr. Gray, you were saying that you got something entirely different though, right?
Yeah, I did the equation. I did the 235 kilo ohms over 3 milliseconds times, I changed it to 256, but I left the 1 millisecond in there and ended up getting, I redid it with 256 and got like 20 something.
All right, so you're letting your calculator take care of that integration for you, is what you're saying, right?
No, I didn't do the integrate. I just plugged in the 1 millisecond and converted everything to base units like ohms and seconds, and then did it like that. The way I typed it in, I did 235 times 10 to the 3 divided by 3 times 10 to the negative 3 times 256 times 10 to the negative 6 times 1 times 10 to the negative 3, and then so on, and did it like that. I left that 1 millisecond in there is what I was trying to say.
Okay. So let me try doing what you're suggesting. So 235 times 10 to the 3 divided by 3 times 10 to the minus 3. Then we would have 256 times 10 to the minus 6.
I figured out my problem. I left a parenthesis out.
Oh, okay.
Yeah, I didn't realize that 235 over 3 was divided or multiplied by the whole entire thing.
Yes, yeah, it's multiplied by the whole thing there. Absolutely. Okay, so that's part A of that problem, and I feel like that guy was fairly straightforward. Part B, we're given a different waveform. And I'm going to leave part C for you guys to do. So in this particular waveform, we still have that R is equal to 235 kilo ohms. Here's our current, I'm going to call it IB of T measured in milliamps. Here's our time, T measured in milliseconds. And then our waveform looks like this. So it starts at 9.5 and goes down to 0 at T is equal to 9. Then it goes back up to 9.5 at T is equal to 18 seconds. Then it comes back down to 0 at 27 and just repeats over and over and over again. So we are going to be using P of T is equal to 1 over T integral from 0 to T of I squared T, R over T, integral 0 to T, I squared T dt. All right, so there's two ways that we can approach this problem. One is more formal, but it's a little bit harder. And the other involves, I'll call it a smidge of intuition, okay? So our average power is going to be R 235 kilo ohms divided by our period, which in this case, our period is what?
9 milliseconds.
I disagree.
It'd be 18 milliseconds.
18 milliseconds, yeah. So it's 18 milliseconds because to go from the top peak, its maximum value of 9.5 back to 9.5 takes 18 milliseconds. So that's our period. Now we have another piecewise function, so I'm going to split it up over two integrals. So the first will be from 0 to 9 milliseconds. And I need to figure out how to describe this waveform as a function of time. So I would argue that it's a straight line, so it should be in the y is equal to mx plus b format, right? So just a slope intercept form. So what is the slope of this guy?
Minus 9.5 over 9.
So minus 9.5 milliamps for every 9 milliseconds. Just you got to keep track of these units and stuff like that, because we're going to wind up squaring things in a moment. And if we don't keep track of the units, it's going to get real weird real fast. Times t. And then what is our y-intercept?
Positive 9.5 milliamps.
All right. And then we square this guy. And then we're going to have an integral from 9 milliseconds to 18 milliseconds. And we need to do effectively the exact same thing. So our slope in this case is going to be positive 9.5 milliamps divided by 9 milliseconds. And what I'm about to do is effectively I'm using a time shifting theorem that you guys should have learned in your pre-calculus, but I understand that you're almost never familiar with it. So what I am saying, I'm effectively making t is equal to 9 my new origin, so that I have a slope of 9 milliseconds. I have a y-intercept at t is equal to 9 of 0 milliamps. And because I've shifted this guy 9 milliseconds to the right, I'm going to do t minus 9 milliseconds as my variable. So it's now in that y is equal to mx plus b format, shifted 9 units to the right. Oh, and I forgot to put in my dt here. So I'll put it here. And then I need to close my brackets. So this is the formal way to do it. Now, the informal way to do this guy would be to recognize that when I integrate the square of this area, it is exactly the same as the square of this area. So I could either do this, or I could effectively truncate this guy like this. They're going to wind up giving us the exact same answer, but the way that I've done it on top is, I would call it the more correct way to do it. But it will wind up giving you the exact same answer either way. So
Where did you come up with that negative 9.5 milliamp over a millisecond t? Could you explain that value real quick?
that's the slope from up here.
Yeah, I seen that, but shouldn't it have been Like negative 9.5 over 9? Or am I just,
Oh, yes. I'm sorry. I see what you're saying. Yes, you're absolutely correct. Negative 9.5 over 9. Thank you. That was just me transcribing it incorrectly. Thank you. So, I'm trying to decide if I want to suffer through doing this integration by hand or literally just throw it in a calculator because we have calculators that are capable of doing this. I'm leaning more towards throwing it in a calculator that is capable of doing this. So what I'm going to do to that end, I'm going to work both of these, but I'm going to break it down into parts to show you how and why it works out. So the first thing that I'm going to do is I'm going to take that 235 kilo ohm over 18 milliseconds and get a number. So that is going to be 1.305 repeating times 10 to the -7 volts per amp seconds. Then I'm going to integrate from 0 to 0.009 negative 9.5 times 10 to the -3 over 9 times 10 to the -3 x plus 9.5 times 10 to the -3 I need to square this whole thing and didn't put quite enough parentheses in it. So let's put another one out front here. And for this first part, I get 2.71 times 10 to the 3, 6, 7, 8 -8. And this should be in, so let's see, I have milliamps per milliseconds times milliseconds is going to be, I took care of that. So this should be amps. Well, I'm trying to think, amps squared. Seconds. And now I need to do the integral from 0.009 to 0.018 9.5 times 10 to the -3 over 9 times 10 to the -3 x minus 0.009 square that. And I get exactly 2.71 times 10 to the minus 8, sorry. Amp squared seconds again. So like I said, the area under those both portions of the curve represents the exact same thing. So times 2 times 1.305 times 10 to the minus 7. Sorry, that should be positive 7. My mistake. Seven 0.0665 watts. Yeah. So obviously then, if I did it the other way, where I effectively just double the area of the first triangle, that's going to be this part plus this part is equal to twice this. So they're the same thing. Excuse me. So that one's about as hard as it can get. I wouldn't ask you anything like that on your exam, just because I'm fully aware that most of you guys aren't comfortable with this time shifting that I did here to express the area of my second triangle. There is a part C to this problem where you're asked to calculate the average power delivered to that resistor with a periodic waveform that is exactly 1/4 of a sine wave. That is more in line with what I would ask you to do on an exam, because you don't have to break up the waveform into a piecewise function at all. So I'm not going to work this one out, but I'll kind of set it up. We only have a couple of minutes left. So if we had I of t that was like this, so it had a maximum value of 6 milliamps, and in 5 milliseconds it rose to its maximum value, and then in another 5 milliseconds it got back up. Like that, we could easily see that I of t, so let's see, how would we, in this case, the period t is 5 milliseconds, right? But we would describe this function as 6 sine omega t, and we just be integrated over that interval from 0 to 5. So how do we find omega here? Anybody have any thoughts before we run out of time in roughly 1 minute? So, Mr. Gray, I'm gonna pick on you slightly. How did we do it yesterday when we had a 1/4 of a sine wave for homework problem 19, homework set 19, problem 3? Because we're asked to do the exact same thing here.
Well, I just found out how I did it, or how we're supposed to find that omega, because you can do 2 pi over t and that'll give you your omega.
Right.
But for the one, sorry.
So in this case, the t isn't 5 milliseconds. T would be 20 milliseconds, right? Because we know that from the perspective of a full sine wave, this guy right here, I'm going to call it would be T prime over 4. And we want 2 pi over what I'm calling T prime there. Does that make sense?
Mm-hmm.
And then from there, so we'd have 6 sine of, so let's see, omega is going to be 2 pi over 20 milliseconds times T. There's no phase angle or anything like that to worry about, milliamps. And so our power, sorry, we're doing average power, would be 235 kiloohms over 5 milliseconds times the integral of 0 to 5 milliseconds, 6 sine 2 pi over 20 milliseconds T squared dt. And then we could use that trig identity and say that this is going to be the integral over 5 milliseconds of 1/2. So let's see, when I multiply a sine by a sine, let's call this 6 cosine 2 pi over 20 milliseconds minus 90 degrees so that I can avoid having to look up another identity. So that would be 1/2 times 6 milliamps squared the resistor bit's already taken out, so I think that, so yeah, plus 1/2 times 6 milliamps squared cosine 4 pi over 20 milliseconds T minus 180 degrees dt. Well, when we integrate this guy over an integer number of periods, this whole thing is going to go away, and we're just going to be left with that 1/2 times 6 milliamp squared term. So, anywho, something like that would be more in line with what I would ask you to do on the exam. Less so the previous 2 problems where we have to break it up into a piecewise function and all that kind of stuff. But I would be more inclined to give you the cosine function directly so that you didn't have to go through the effort of converting the sine to cosine and then applying your trig identity and all that kind of junk. Anyway, I ran a couple of minutes long, so unless anybody has any questions, I'm done talking about stuff today, but I'm happy to stay on and answer any questions if anybody has any.